Hello students. So today we will discuss how to prepare potassium permanganate and potassium dichromate. Let us see first potassium permanganate. Potassium permanganate. KMnO4. It is considered what a salt of permanganic acid. Salt of permanganic acid, HMnO4. Generally, potassium permanganate is prepared from pyrolusite. It is an ore of manganese. From preparation from pyrolusite. From pyrolusite, it is an ore of manganese. Steps involved in this. Steps involved in the preparation of permanganate from pyrolusite. This pyrolusite, first we have to convert into potassium manganate KMnO4 in the first step. The second step, it is converted into potassium permanganate KMnO4. Pyrolusite in the first step converted to potassium manganate, and in the second step converted into potassium permanganate. This is potassium manganate. Potassium manganate. This is actually green in color, green. This is potassium permanganate. Potassium permanganate. It is purple in color. It is purple in color. Now let us see how to prepare first potassium manganate and followed by potassium permanganate. Step 1. Step 1. Pyrolusite MnO2 fused with pyrolusite fused with KOH or by potassium carbonate in presence of atmospheric oxygen. In presence of atmospheric oxygen. First potassium manganate is produced and then potassium manganate oxidized to potassium permanganate. Let us see the first step, how pyrolusite can be convertible into potassium manganate. 2MnO2 plus fused with KOH plus atmospheric oxygen. Then you have to get first potassium manganate. Let us see this one, 2KMnO4. 2KMnO4 plus H2O. First you are getting 2K2MnO4. Pyrolusite converted into water, potassium manganate. The first way of conversion, pyrolusite fused with KOH, we are getting what? Potassium manganate. Second way of conversion of pyrolusite to potassium manganate, similarly 2MnO2 plus 2K2CO3 in presence of oxygen. Again you are getting potassium manganate, then it will be 2K2MnO4 plus 2K2MnO4 plus 2CO2. Like this, pyrolusite first, the first step converted to potassium manganate. Next step, potassium manganate converted into potassium permanganate. Let us see the second step. Now, potassium manganate KMnO4 to potassium permanganate. potassium manganate to potassium permanganate. Now, for this potassium manganate oxidized by either it may be chlorine or it may be by ozone or it may be by carbon dioxide. Potassium manganate oxidized by chlorine or ozone or CO2. Now 2K2MnO4 potassium manganate plus consider Cl2, then you are getting 2KMnO4 potassium permanganate plus 2KCl. Similarly, second way of conversion of potassium manganate to potassium permanganate by oxidation with ozone. Consider then it is 2K2MnO4 plus ozone in presence of water. Then also you are getting potassium permanganate to KMnO4 plus 2KOH plus O2. 2KOH plus O2. Similarly, you can also convert potassium manganate to potassium permanganate by using CO2. Third way of conversion, consider 3K2MnO4 potassium manganate plus 2 CO2, then you can also convert into potassium permanganate, then it is 2KMnO4 plus 2K2CO3 plus it is again MnO2. Like this, potassium manganate convertible to potassium permanganate by using chlorine or ozone or CO2. In this way, first step, pyrolusite converted to potassium manganate and potassium manganate oxidized to potassium permanganate by all means, either it may be chlorine gas or it may be by ozone gas or it may be by CO2 gas. In this way, we are generally producing potassium permanganate. Next we see how to prepare potassium dichromate commercially. Next we see the preparation of potassium dichromate commercially. Now let us see the preparation of potassium dichromate. Potassium dichromate you know K2Cr2O7 potassium dichromate. Potassium dichromate generally prepared from chromator. From chromator, you know the formula of chromator FeOCr2O3. Generally, potassium dichromate prepared from chromator. It is also within 3 steps. Now, potassium dichromate from chromator we can prepare in 3 steps. Let us see what are the steps involved in the preparation of potassium dichromate from chromator. Now, chromator FeOCr2O3, in the first step we are converting into sodium chromate Na2CrO4 in the first step. After getting sodium chromate, in the second step this is converted into sodium dichromate Cr2O7. Chromator, in the first step you are converting into sodium chromate. Sodium chromate, in the second step you are converting into sodium dichromate, and sodium dichromate we can convert into again potassium dichromate. In the third step we are getting potassium dichromate. So chromator first converted to sodium chromate. Sodium chromate in the second step converted to sodium dichromate. Sodium dichromate in the third step converted to potassium dichromate. Let us see in what way we can convert chromate ore to potassium dichromate in 3 steps. Let us take the step 1. Step 1. Now, chromate ore we are converting into sodium chromate. Let us see now. For FeOCr2O3, this is fused with sodium carbonate. fused with sodium carbonate in presence of oxygen, roasted in air, then this chromate ore converts into sodium chromate, then it is 8 Na2 CrO4 plus, then you are getting here 8 CO2 plus 2 Fe2O3. The first step, chromate ore converted into sodium chromate. Let us come to the second step, step 2. Sodium chromate converted to sodium dichromate. It is very simple. Now 2Na2 CrO4 treated with what? Sulfuric acid. Then you are getting it is sodium dichromate. You are getting Na2 Cr2 O7 plus you are getting Na2SO4. Like this, sodium chromate converted to what? Sodium dichromate. The next step, sodium dichromate we convert into sodium dichromate converted to what? Potassium dichromate. Step 3. This particular sodium dichromate Na2 Cr2O7 treated with what? KCl. Then simply potassium ion substituting sodium ions, then you are getting simply it is K2 Cr2O7 plus 2 NaCl. Like this, first you are getting sodium chromate, the second sodium dichromate and potassium dichromate. In this way, commercially we are preparing potassium dichromate from chromate ore. So these two are the methods of preparation of potassium permanganate and potassium dichromate are very important for your IIT, either it may be mains or it may be for IIT advanced examinations. So these are very important. Remember easy way how to convert in the case of potassium dichromate chromate ore to potassium dichromate. In the case of potassium permanganate, how we convert pyrolusite ore to what? Potassium permanganate. F block elements. Inner transition elements. Inner transition elements. F block elements or inner transition elements. Let me introduce what are actually F block elements, inner transition elements, and how many series of this particular inner transition elements, what are their general electronic configurations. We will discuss it. Now, look at here, this particular F block elements in the modern periodic table starting from 6th period. Let us see how. Now we consider hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Let us see this first period, second period, third period, fourth period, fifth period. Let us consider to sixth period and again seventh period. So these elements are starting from sixth period I said. Now atomic number of cesium is what? 55. After 55 the element is what? Barium. It is what? 56. After 56 you are getting lanthanum. Lanthanum is what? 57. Lanthanum to hafnium. Then in between lanthanum to hafnium, this is what? 72. In between this particular lanthanum to hafnium, the elements actually cerium to lutetium. It is 58 to lutetium 71. This particular cerium to lutetium 58th element to 71st element considered as actually these are, you can consider lanthanides to say, or 4F series, or we can consider as what? First inner transition series. Now let us consider in the case of 7th period, this is what? Francium 87. After 87 it is what? Radium 88. 87, 88. After 88 you can say it is what? 87, 88. Next element is what? Actinium. Next element is actinium 89. This is what? Actinium. Actinium 2, this is what? Rutherfordium. This is what? 89 and again 104. In between this 89 to 104 Rutherfordium, the 14 elements again thorium 90 to what? Lawrencium 103. This is what? Thorium 90 to Lawrencium 103 are known as what? Actinides, or known as actinides, or you can take 5F series, or you can consider second inner transition series. Second inner transition series. Like this, first series is what? Cerium 58 to lutetium 71. These are what? Lanthanides. 4F series, first inner transition series. Second series, thorium 92, Lawrencium 103. These are what you call actinides, and 5F series and second inner transition series. So what I said, in the periodic table, this F block elements starting from what? 60th period. 60th period, and in both 7th period, we are observing this particular this lanthanides and actinides, or F block of elements. Next, let us see what are the definitions of F block elements and what are inner transition elements, what are their general electronic configuration. Let us discuss this. Now let me introduce F block elements. F block elements. Now we are talking about this particular 60th period. 60th period. Now we consider in the periodic table, each period is a shell. Once you are talking about the 6th period, you have to write 6 shells. Now you are talking about a 6th shell. 6th period means 6th shell in the atomic structure. 6th shell in the atomic structure you take. Now first shell, second shell, third shell, fourth shell, fifth shell, and the 6th shell let us consider. Now this is what? Hydrogen. It is what? This first shell group of elements NS1. This is what? 1s1, 2s1, 3s1, 4s1, 5s1. This is coming to be what? 6s1. After 6s1, this one will be 6s2. After 6s2, this will be 5d1. 5d1. After 5d1, this is coming to be 4f1, and this is coming to be 4f14. 4f1 to 4f14. Let me write. Now this is what? 6s1 and 6s2 valence shell electronic configuration. Next, lanthanum, you can say it is what? 5d1. 5d1. So this is after S block element, you are coming across this particular lanthanum. This is what? 5d1. After 57th element lanthanum, the electrons from 58 to this is what? 71. 58 to 71, these are all what we consider differentiating electron. This particular differentiating electrons, where they are entering, let us check it. Now 58th electron, let us consider 58th electron to 71st electron. These electrons are not entering into the valence shell, no. And these are electrons also not entering into d orbitals. These are entering into what? 58 to 71st electron. These electrons are actually entering into f orbitals of the anti-penultimate shell. F orbitals of anti-penultimate shell. So the elements in which the differentiating electron, enter into f orbitals of anti-penultimate shell are known as what? F block of elements. The elements in which the differentiating electrons entering into f orbitals of anti-penultimate shell are known as what? F block of elements. Let us see what are inner transition elements. Inner transition elements. Inner transition elements. Inner transition elements. Now, the elements which are carrying incompletely filled n-2 f orbitals, which are carrying incompletely filled n-2 f orbitals, let me say 1 to 13. The element which are carrying incompletely filled n-2 f orbitals, either in their atomic state, consider in their atomic state, or in their chemically significant oxidation states. Chemically significant oxidation states. The element which are carrying incompletely filled n-2 f orbitals in their atomic state or in their chemically significant oxidation states are known as what? Inner transition elements. In a single word, inner transition elements means the elements which are carrying incompletely filled f orbitals are known as what? This inner transition element. Transition elements means which are carrying incompletely filled d orbital. Inner transition means which are carrying incompletely filled f orbitals. We can consider these are what? Inner transition. Now, either you consider f block elements or you consider inner transition elements. In f block elements or inner transition elements, the orbitals of the valence shell, penultimate shell and antipenultimate shell, all the three shells of orbitals found to be incompletely filled. What I am saying, in the case of f block elements or inner transition elements, the orbital of the valence shell, penultimate shell, antipenultimate shell, these three shells are carrying incompletely filled orbital. How? Now you talk about this particular 6s2, what about 6p? 6p is not carrying any electron. 6p is not carrying any electron. And 5d1, in the case of d orbitals, they are incompletely filled. Now you talk about only in the 14th element, the electronic configuration is what? F14. What about the 13th element of lanthanide? Lanthanide 13th element carrying what? F13 configuration. Means what? The orbital of the valence shell, penultimate shell, antipenultimate shell, all the three orbitals of all the three shells are incompletely filled. Therefore, in f block elements, in inner transition element, the orbital of the valence shell, penultimate shell, antipenultimate shell, all the three are found to be incompletely filled. Next, let us see how many series of these elements, how they are classified into lanthanides and actinides, and what are their general electronic configurations. See, f block elements are classified into two series. F block of elements are classified into two series. F block of elements are classified into two series. Let me say A. The 14 elements of third B group. The 14 elements of third B group and sixth period. The 14 elements of third B group and sixth period, starting from cerium 58 to lutetium 71. Cerium 58 to lutetium 71 are known as what? We can say lanthanides, or you can consider 4F series, or you can say first inner transition series. Next, coming to second series, the 14 elements of third B group, actinides also belonging to third B group. The 14 elements of third B group, seventh period, starting from thorium 90 to lawrencium 103. Thorium 90 to lawrencium 103 are known as what? These elements are known as what? Actinides to say, or 5F series, or second inner transition series. Like this particular F block elements are classified into two series, that is lanthanides 4F series, first inner transition series, actinides 5F series, and second inner transition series. Let us see what are their general electronic configurations. General electronic configurations of this lanthanides and actinides. While showing the general electronic configuration, we have to show this particular valence shell NS2. Let me say N-1 D. In some of the elements it is 1, in some of the elements it is 0. 1, 0 we can write, and it is N-2 F 1 to 14. The general electronic configuration of lanthanides is what? NS2, N-1, D01 and N-2 F 1 to 14. The same configuration you can also represent in different way by representing this particular xenon. Why we are writing xenon? After xenon 54 you are getting 55 and 56 followed by lanthanides. Therefore, xenon we can write is what? NS2 N-1 D01 and N-2 F 1 to 14 you can write. Another way of the representation of this particular general electronic configuration, showing the real orbit numbers. Let me see, this is what xenon subshells number, you can take it is what 6s2 and 5d10, or we can say it is what 4f1 to 14. Like this, the general electronic config lanthanides can be represented in the three ways. It is NS2 n-1 D01 1 to 14 and xenon NS2 n-1 D01 n-2 F1 to 14, and here giving the shell number or subshells number xenon 6s2 5 D01 and 4F 1 to 14. Either the way you can represent the general electronic configuration of lanthanides. That generally it can be given in the examination in a brief manner. That is what it is: NS2 n-1 D01, or it is what n-2 F1 to 14, or simply they mention S2 D1 and F1. Like this also they are mentioning the electronic configuration. Either the way you can represent the general electronic configuration of lanthanides. Coming to actinides, consider this as the lanthanide general electronic configuration. Consider this is what actinide general electronic configuration. Similar way of representation for actinides also. Let me write the same way: NS2 n-1 you can write D01 and n-2 F1 to 14. Similarly, you can also write this particular general electron configuration. Instead of writing xenon, let me say it is what radon and NS2 n-1 D01 and n-2 F1 to 14. And we can also write the third way of representation. Now we can write giving the subshells number here, then radon, instead of writing 6s2, let me say 7s2 and 6 D01 and 5F1 to 14, 5F1 to 14. So this is the general electronic configurations of actinides represented like this. This is actinides represented like this. So this is what two series of elements and general electronic configurations of lanthanides and actinides. Some brief properties of this particular lanthanides. Let me introduce some important properties of lanthanides. Now, the lanthanides are actually active metals. Remember, these are active metals. Next, these are strong reducing agents. These are strong reducing agents, active metals and strong reducing agents. Their electrode potential values are actually negative. Their electrode potential values are negative, and they are having more negative reduction potential values. Therefore, they are acting as what strong reducing agent, and they easily liberate hydrogen gas from either it may be from dilute acids or it may be from hot water. Dilute acids and also from hot water, these are easily liberating hydrogen gas. So, lanthanides are active metals and these are strong reducing agents, and their electrode potential values are negative, and again they are easily liberating hydrogen gas from dilute acids and also from hot water. These are all the properties of active metal. So, their properties are active metallic property. Their properties are much more similar to either first A group, second A group and like third A group of element like aluminum. So, the properties of this particular lanthanides little bit similar to first A group, second A group and again aluminum. Like this, some of the properties of these elements are similar to first A, second A and aluminum. This is the brief introduction about this particular lanthanides and actinides or AF block of elements. See, now let us discuss properties of lanthanides. Properties of lanthanides. Let us discuss the first property. Let us say oxidation states of lanthanides. Oxidation states. The common and stable oxidation state of lanthanides is +3. The common and stable oxidation state of lanthanides is +3. Why all these particular lanthanides, 14 lanthanides commonly exhibit the +3 oxidation state? What are the reasons for it? Let me say it is due to what? Their lattice energies. This is due to what? In solid state. In solid state, the lattice energies, or in aqueous solutions. In aqueous solutions. In aqueous solutions, the heat of hydration values. in solid state the lattice energies, and in aqueous solutions the heat of addition values. These two are much more compensating first 3 IP values. That means what? First IP you take, second IP you take, and third IP you take. So the lattice energies, in solid state the lattice energies, and in aqueous solution the heat of addition, these two energy values are much more compensating first 3 IP values. Therefore, they are easily losing the first electron and again second electron and third electron, but it is difficult to lose the fourth electron. This is difficult to lose the fourth electron. Therefore, they are exhibiting commonly as what? +3 oxidation state. Next, in addition to +3 oxidation state, few of the elements exhibiting +2 and +4. Why they exhibit +2 and +4 in addition to +3? Now let us see some of the elements are exhibiting in addition to +3, +2 oxidation state and also +4 oxidation state. This +2 and +4 only possible when this particular lanthanide ions are gaining either stable F0 configuration or F7 configuration or F14 configuration. Let us consider some of the examples. We can take here europium +2. In addition to +3, europium also exhibiting +2. Similarly, the another element ytterbium also exhibiting +2. So why europium +2 and ytterbium +2 still they are exhibiting in addition to +3? Europium +2 you see it is actually F7 configuration. Ytterbium +2 you see it is actually F14 configuration. So in addition to +3, one or two elements are exhibiting this particular +2 oxidation state, because in +2 they are gaining stable F7 configuration and again stable F14 configuration. Some of the elements also exhibiting in addition to +3, +4 oxidation state. Which elements are exhibiting this +4 oxidation state? Let us consider cerium +4 is there and again terbium +4 is there. These two elements exhibiting +4 oxidation state in addition to +3. Why? In their +4 oxidation state they are gaining stable F0 or they are gaining what? Stable F7 configuration. What I said? Common and stable oxidation state of lanthanides is +3. This is due to in solid state the lattice energies, in aqueous solutions heat of addition values. These two energy values are compensating the first 3 IP values. Therefore, they are easily losing 3 electrons, but the losing of 4th electron is difficult. Therefore, all of these 14 lanthanides exhibiting the stable and common oxidation state as +3. But few elements in addition to +3 exhibiting +2 and +4. Why they are exhibiting +2 and +4? In their +2 and +4 oxidation state, if they are gaining stable F0 configuration or F7 configuration or F14 configuration, these elements are exhibiting this +2 and +4 oxidation state. Because they are gaining, look at here, the stable either F0 or F7 or F14 electronic configurations. Next we see the other thing. Once you are taking samarium +2 and ytterbium +2 and europium +2 you take. Samarium +2, ytterbium +2 and europium +2 you take. Samarium electronic configuration is what? F6 configuration. Ytterbium +2 is what? F14 configuration, and europium +2 is what? F7 configuration. Samarium +2, ytterbium +2 and europium +2 you consider their electronic configurations are F6, F14 and F7 electronic configuration. The order of stability of this particular electronic configurations, you can take order of stability. Order of stability of these electronic configurations, you can say this F6, let me say samarium +2 is less stable than ytterbium +2, less stable than europium +2. Here in the case of F14 is less stable than F7, we are saying, look at here, whenever F subcell is carrying 14 electrons, 14 units of electronic charge accumulated in the single subcell, then there will be greater interelectronic repulsions. Therefore, F14 is actually less stable than what? F7. This is order of stability of this particular 3 ions. Next, Order of reducing power you take. Order of reducing power. Order of reducing power of these. Order of reducing power of these. You consider this. Samarium plus 2 is what? Strong reducing agent. Then ytterbium plus 2. Then europium plus 2. Europium plus 2. How can you say that this particular order? Whichever the ion is least stable, that will be strong reducing agent. Therefore, samarium plus 2 is less stable than ytterbium. Ytterbium less stable than europium. Therefore, samarium is a stronger reducing agent than ytterbium, stronger reducing agent than europium. This is the order of stability and order of reducing power. In the examination, these 2 points are important. What is the common oxygen state of lanthanide? Common oxygen state of lanthanides is +3, first point. Second, generally they give these particular 3 ions. They will ask you what is the order of stability of these 3 ions and order of reducing power of these particular 3 ions. This is the order of stability. This is what order of reducing power of these particular 3 ions. The very important points. Only first point, common oxygen state and order of this stability and reducing power of these particular 3 ions about this particular oxidation states. Next, let us have a discussion about magnetic properties. Magnetic properties of lanthanides. Magnetic properties. Magnetic properties. See, most of the lanthanides you take, their compounds you take. Most of the lanthanides and their compounds exhibiting paramagnetic property. Why they exhibit paramagnetic property? Because of presence of unpaired electrons in f orbital. Because of presence of unpaired electrons in f orbital. Unpaired electrons in f orbital, they are exhibiting paramagnetic property. Paramagnetic property. Next, you can say either you consider F0 configuration or F14 configuration. These particular 2 configurations are diamagnetic. Diamagnetic. Why? F0 no unpaired electron, F14 no unpaired electron. Therefore, F0 and F14 electronic configurations are found to be diamagnetic. Now you consider in the case of total paramagnetic moment. Total paramagnetic moment to take. Total paramagnetic moment equal to already given in D block elements. Also, let us consider spin angular moment plus orbital angular moment. Total paramagnetic moment equal to spin angular moment plus orbital angular moment. This we can show with a equation nu s plus L is equal to under root of, you can take 4s into s plus 1 L into L plus 1. This is the equation we apply for the calculation of total paramagnetic moment of any atom or the compound. This stands for spin angular moment. This stands for orbital angular moment. Once you consider D block elements, especially in 3D series, D block elements, especially in 3D series, the orbital angular moment is quenched by the ligand fields. This orbital angular moment is quenched by the ligand fields. Therefore, you need not consider this particular orbital angular moment for the calculation of total paramagnetic moment of D block elements, especially 3D series. But in the case of F block elements of lanthanides, this particular orbital angular moment is not quenched by the ligand fields. Not quenched by the ligand fields. Why? This orbital angular moment is not quenched by the ligand field. Look here, in the case of F orbitals are deeply seated in the anti-penultimate shell. Look the board for a while, you can easily understand what is this. 1, 2, 3rd, 4th, 5th and 6th shell you are writing. Now in the case of this particular 6s2, and we write the configuration as 5d1 and let us take 4f1 14. 4f1 14. Let us consider ligand is here. Ligand is actually near to d orbital. Ligand is near to d orbital, therefore ligand field is affecting the orbital angular moment of electrons in d orbitals. But in the case of f orbitals, you are clearly looking this ligand is away from f orbital. So f orbitals are deeply seated in the anti-penultimate shell. As a result, the orbital angular moment of electrons in f orbitals not affected by the ligands because ligands are away from the f orbital. Therefore, the total equation you have to use for the calculation of total paramagnetic moment of the F block elements or lanthanide elements. What I said, in the case of D block, the orbital angular moment is quenched by the ligand fields, especially in 3D series. But in the case of lanthanides or F block elements, the orbital angular moment is not quenched by the ligand fields because F orbitals are deeply seated, not affected by the ligand fields. Therefore, total equation you have to apply to calculate the total paramagnetic moment of this particular lanthanides or F block elements. Now, recently by the combination of this particular orbital angular moment and spin angular moment, orbital angular moment and spin angular moment, a new quantum number was introduced. Actually, we know 4 quantum numbers well known to us: principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. But recently a new quantum number was introduced, that is what this by the combination of this spin angular moment and orbital angular moment, new quantum number was introduced, that is represented by what capital G. Capital G. What is this? The resultant quantum number of spin angular moment and orbital angular moment. Resultant quantum number of spin angular moment and orbital angular moment. It is represented by capital G. Therefore, instead of using such a big equation, you can apply a small equation. Now, nu effective is equal to G into under root of J into J plus 1. J into J plus 1. This G is what nothing but already given in the D block elements also. The G stands for gyromagnetic ratio. Its value is what 2. And J stands for resultant of both this particular spin angular moment and again orbital angular moment. Next point. Now, which element among the lanthanides exhibiting greater paramagnetic moment? Generally, the element of the compound which is carrying more number of unpaired electrons, that will be exhibiting greater paramagnetic moment. The element of the compound carrying more number of unpaired electrons, that will be exhibiting greater paramagnetic moment. If you consider the same point, among all the lanthanides, gadolinium is carrying maximum number of unpaired electrons. Its configuration is what F7 D1. Its configuration is F7 and D1. Total number of unpaired electrons coming to be what 8. According to number of unpaired electrons among the lanthanides, gadolinium has to exhibit greater paramagnetic moment. But experimental results show that it is not exhibiting greater paramagnetic moment. Among the lanthanides, the greater paramagnetic moment is observed with only dysprosium. Only observed with dysprosium. Second element is what holmium. Second element is holmium. So why dysprosium and holmium are exhibiting greater paramagnetic moment, even though the number of unpaired electrons in dysprosium and holmium are less in comparison to gadolinium. Next, whenever F sub shell is half filled or less than half filled, whenever F sub shell is half filled we take, or less than half filled like 6 and F5. It is half filled or less than half filled, then the spin angular moment and orbital angular moment both are working in opposite directions. Whenever F sub shell is less than half filled or half filled like this, then the spin angular moment and orbital angular moment both are working in opposite directions. But F7 we see in gadolinium. Therefore, in this, the spin angular moment and orbital angular moment both are working in opposite directions. Therefore, paramagnetic moment in the case of gadolinium is less. Whenever F sub shell is more than half filled, consider it may be F7 or F8 or F9. Whenever F sub shell is more than half filled, consider F7, F8, F9. Then the spin angular moment and orbital angular moment working in the same direction. Therefore, it is considered what L plus S. Because of this particular reason, even though gadolinium is carrying maximum number of unpaired electrons, but it is exhibiting less paramagnetic moment among the lanthanides. Highest paramagnetic moment among the lanthanides is observed in dysprosium. Second is what holmium. First is dysprosium. Second is holmium. This is about magnetic properties of this particular lanthanides. Next, let us see color properties of lanthanides. let us discuss about color properties of lanthanide elements. Most of the lanthanides and their compounds. Most of the lanthanides and their compounds exhibit color. Most of the lanthanides and their compounds exhibit color. It is due to presence of unpaired electrons in f orbitals. Unpaired electrons in f orbitals. It is also due to f orbital to f orbital electronic transitions. It is also due to f orbital to f orbital electronic transitions. Most of the lanthanides and their compounds exhibit color. It is due to presence of unpaired electrons in f orbitals and also due to f orbital to f orbital electronic transitions. Now you consider either you take F0 configuration or F14 configuration. Yes, they are not carrying any unpaired electrons, therefore they are not exhibiting color. These F0 and F14 compounds, F0 and F14 compounds, or you take F0 and F14 electronic configurations of lanthanides are generally not exhibiting any color. They are found to be colorless. Now we consider similarly, if you talk about F1 configuration and F13 configuration, look at here. This F1 configuration and F13 configuration, F1 and F13 configuration, still they are carrying unpaired electrons, but they are not exhibiting color. They are also found to be colorless. Even though they are carrying unpaired electrons, still F1 and F13 are not exhibiting color. It is due to infrared absorption of infrared absorption. For this particular F1 and F13, due to infrared absorption, these two electronic configurations of lanthanides are not exhibiting color. Coming to the next point to see, F7 electronic configuration is also found to be colorless. This particular F7 electronic configuration, wherever F7 electronic configuration is there, 7 unpaired electrons are there. Still, in the case of F7 electronic configuration, lanthanide compounds are not exhibiting color. It is due to what? UV absorption. So F1 and F13, even though unpaired electron they are carrying, still they are colorless. Similarly, in the case of F7, still they are colorless. In the case of F1 and F13, it is due to infrared absorption, and F7 electronic configuration due to F7 electronic configuration it is due to UV absorption. Even though they are carrying unpaired electrons, they are not exhibiting color. Next, in the case of lanthanides, the F1 ions, Fn ions and F14 minus N ions. Fn ions and F14 minus ions means, now you consider the lanthanide ions which are carrying same number of unpaired electrons. The lanthanide ions which are carrying same number of unpaired electrons. The lanthanide ions which are carrying same number of unpaired electrons, the pairs are found to be having more or less same color. More or less same color. Now let me show you a table here. All the 14 lanthanides we can make into 7 pairs. All these particular 7 pairs are carrying same number of unpaired electrons and their color is also found to be more or less identical. Let me show by a table how this particular 14 lanthanides we can make into 7 pairs, and the 7 pairs are having more or less same number of unpaired electrons. Once unpaired electrons are same, their color is also found to be identical. I will show a table carrying this particular 7 pairs of lanthanides now. See, let me make a table, all the 14 lanthanides into 7 pairs. Let us see now. Let us make it Fn ions, number of unpaired electrons, number of unpaired electrons, number of unpaired electrons, and F14 minus N ions, F14 minus N ions, Fn ions, number of unpaired electrons, F14 minus N ions. Let me make one more column. What is the color of this particular pairs? So Fn ions, F14 minus N ions, and color of this. But for this you have to remember compulsory all the 14 lanthanides. It is better to make this particular table. Otherwise it is difficult whenever a question appears in the examination. Once you remember all the 14 lanthanides, you can easily make this particular table. What is my advice is compulsory it is better to remember all the 14 lanthanides, then only you can make easily this particular table. You can easily answer in the examination. It's very, very important this particular table. Many times the repeatedly a question appearing on this particular table and color properties of lanthanides. Let me make a table. You observe this now. cerium, praseodymium, neodymium, promethium, samarium, and europium. Let me write gadolinium. Up to 7 elements are written: cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium. Next, we have to start again a similar way. Gadolinium to the last element. Like this, we can make a 7 pairs of this particular lanthanides. Again, I am starting from down to again up. Now, gadolinium to again the last element I am showing to you. We observe this particular gadolinium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, and ytterbium. Like this, all the 14 lanthanides we can make into what 7 pairs. Now we are talking about ions. Let me make all the lanthanide ions are exhibiting a common oxygen state of +3. Let us consider all are +3. All are +3 ions. Let us make it. Then we can easily say these are all carrying actually same number of 100 electrons. Let us check it now. Gadolinium +3, terbium +3, dysprosium, holmium, erbium, thulium, ytterbium. Now they are all carrying, the pairs are carrying same number of 100 electrons. Check your notes. 1, 2, 3, 4, 5, 6, 7. So all these particular pairs are carrying that same number of 100 electrons, and their color is also found to be more or less identical. Now look at here. This particular, what we said, F1 configuration colorless I said. Therefore the first pair is actually colorless. First pair is actually colorless, and the second pair is actually exhibiting green color. This is second one is what lilac, and third one is actually pink in color, and the fourth one is actually yellow in color, and pale pink in color, pale pink. The last one is also colorless. 7 unpaired electron. Like this, the 14 lanthanides we are making into 7 pairs. As I said, the each pair is carrying what the same number of 100 electrons. When the unpaired electrons are same for a pair, that particular exhibiting more or less identical color. But in what way the question is appearing? Question never appears like this. What is the color of thulium +3 salts? No. Question appears in different way. Let me show how the question appear and how to answer in the examination. For that, what I said, you have to remember all the 14 lanthanide. You should be in a position to make this particular table. Otherwise solving in the examination it becomes difficult. Therefore, you have to remember compulsory all the 14 lanthanides to make this particular table. I will make a sample question how the question appear in the examination. See how the question appears. Samarium +3 salts. Samarium +3 salts are exhibiting what color? Exhibiting yellow color. Exhibiting yellow color. Exhibiting yellow color. Which of the following ion? Which of the following ion can exhibit more or less same color. Question appears like this. The multiple choice they will give like this. Now neodymium +3, let me write neodymium +3, and again you can take promethium +3. Check it, samarium opposite dysprosium. See, let me take dysprosium +3, and you take gadolinium +3. You take. Like this, samarium +3 salts are exhibiting yellow color. Which of the following can exhibit more or less identical or more or less same color? Then once this particular question appears, what is actually given? Samarium +3. You should be in a position to make the table, and you have to see that opposite to samarium, what ion you are getting. See, opposite to samarium, what is the ion you are getting? Dysprosium. Like this, dysprosium is the answer here. Like this, you should be in a position to do such questions in the examination, provided you should be in a position to write this particular table in the examination. Otherwise, difficult to answer such question. But this is actually frequently the color properties on this particular lanthanides every time in one of the entrance exam, this particular question is frequently appearing. You should be very careful about solving this particular type of questions. Right. Now let me discuss the next concept of complex formation by lanthanides. Complex formation. Complex formation and formation of hydrated ions. Complex formation of hydrated ions. Complex formation and formation of hydrated ions. See, in the case of lanthanides, from left to right, consider lanthanum to actually lutetium you take. Lanthanum to lutetium, the atomic and ionic size is gradually decreasing. Now we consider lanthanum plus 3 ion and again lutetium plus 3 ion. Lanthanum plus ion, lutetium plus ion. Left to right, the atomic size and ionic size is decreasing. And charge density is increasing. Now it is having plus 3 charge density, but surface area is more. It is having what lesser charge density, or thickness of the charge is what less over this particular lanthanum ion. But lutetium is what smaller in size. It is having what greater charge density. But you can understand, lanthanum to lutetium, there is actually decrease in ionic size, increase in charge density. Once charge density is increasing, the tendency of formation of ions gradually increasing. So lanthanum to lutetium, due to decrease in ionic size and increase in charge density, the tendency of formation of a complex is gradually increased. Now, if you consider D block elements and again F block elements you take, D and F, D block and F block you consider. The tendency of formation of F block elements is actually less in comparison to D block elements. If you compare D and F block elements, the tendency of formation of complexes by F block elements is found to be less. Why it is less? Now simply you can understand this particular F orbitals. Let me say first shell, second shell, third shell, fourth shell, fifth shell and sixth shell you take. Now in the case of this is actually what we have taken the configuration, say 6s2 and we have written what 5d1, consider 4f. See, the d orbitals are actually near to ligands. The ligand can easily interact with d orbital. See, in the case of if you compare D block and F block of elements, the tendency of formation of complexes by this particular lanthanides is less in comparison to D. Why? See, clearly observe in the case of sixth shell you take, the d orbitals are actually near to the ligands, as d orbitals there in the penultimate shell. But you consider F orbitals, you are clearly looking on the board, F orbitals are deeply seated in the anti-penultimate shell. Therefore, ligand is away from the F orbitals. Therefore, as the way d orbitals interacting with the ligands, similarly F orbitals cannot interact. Therefore, the tendency of formation of complexes by lanthanides is found to be less in comparison to D or D block elements. Next, let us see what is this particular formation of hydrated ions. Now you see, whenever you are putting a metal ion in a particular aqueous solvent you take, you are putting a metal ion in this. Then this particular metal ion occupied by many water molecules. In this way you are getting what hydrated ion. This is what you call hydrated ion. Whenever a metal ion is put into aqueous solvent like water, the water molecules are actually occupying that particular metal ion, then you are getting ion known as what hydrated ion. Now the formation of hydrated ions is take, same concept you can apply whatever the way we are talking about this particular complex formation, similar concept we can discuss here. Now again from lanthanum to lutetium, look at your lanthanum to lutetium. Due to decrease in the ionic size, increase in the charge density, this is having what less charge density, lutetium is having what greater charge density. Due to decrease in the size, increase in the charge density, the tendency of formation of hydrated ions also increase from lanthanum to lutetium. Next, what we can understand, lutetium hydrated ion is actually very big in size. As the charge density is more, lutetium can accommodate the water molecules not only in one layer, it can accommodate first layer, second layer, three layers of water molecules, it can accommodate like this. Therefore, lanthanum to lutetium, the tendency of formation of hydrated ions is increasing. Similarly, lanthanum to lutetium, the sizes of hydrated ions also increasing. Means what you can understand, lutetium hydrodion is very big in size and lanthanum hydrodion is what? Small in size. The same concept is useful to discuss other concept. Let us have a discussion of next concept. So, complex formation and formation of what? Hydrated ions. Next, let us discuss what is lanthanide contraction, what are its effects and all. We will discuss. Next concept what we discuss, lanthanide contraction. Lanthanide contraction, lanthanide contraction. See, in the case of lanthanides, many times I have shown this particular electronic configuration of lanthanides. Once you talk about this particular lanthanides, let us talk about the sixth shell. Let me write 6 shells. First shell, second shell, third shell, fourth shell, fifth shell, and again a sixth shell. Look at here again, electronic configuration also I many times mentioned while discussing about this particular lanthanides. Let me say it is 6s2, 5d1, 4f1 to 14, 4f1 to 14. In the case of lanthanide, the differentiating electrons are actually entering into f orbitals of the antipenultimate shell. In the case of lanthanides or f-lock elements, we talk about lanthanides only. This particular differentiating electron entering into f orbitals of antipenultimate shell. As a result of this, how many electrons are entering? 14 electrons are entering into the antipenultimate shell. Once 14 electrons are entering, similarly 14 units of nuclear charge is increasing. 14 units of nuclear charge is increasing. And increasing the nuclear charge and electrons are entering into what? Antipenultimate shell f orbitals. Once nuclear charge increasing and increasing the and electrons are entering into f orbitals of antipenultimate shell, and moreover fulfilled f orbital or generally f orbitals are pore shielders. Therefore, nuclear charge actually directly working on this particular outermost orbital electron. Nuclear charge directly working on this outermost orbital electron. By this, atoms are gradually contracting. Atoms are gradually contracting. This particular contraction, consider cerium to lutetium. Cerium to lutetium, atoms are showing a gradual contraction in their sizes. This particular size decrease, atomic size decrease, what we call lanthanide contraction. Once again, we listen what is the actual definition of lanthanide contraction. In the case of lanthanides, the differentiating electrons are entering into f orbitals of the antipenultimate shell. As a result of this, there will be increase in the nuclear charge by 14 units. In addition to this, f orbitals are pore shielders. Therefore, the nucleus is actually attracting the outermost orbital electron towards itself. As a result, cerium to lutetium, there is a gradually decrease in the atomic size. This particular decrease we call it as what? Lanthanide contraction. Let us discuss now what are the consequences, what are the results, what are the effects of this particular lanthanide contraction. Consequences of lanthanide contraction. Consequences of lanthanide contraction. Consequence of lanthanide contraction, let us take first one. Recollect while discussing about the D block, you might be knowing this particular. Now, 3D series to 4D series, atomic size increasing, I said, yes, increasing. But 4D to 5D series, the atomic size actually showing a decrease or remaining more or less same. Look at here, 3D to 4D, atomic size increasing, and 4D to 5D, the atomic size remaining more or less same or decreasing. It is due to simply lanthanide contraction effect. Lanthanide contraction effect. Next, 3D to 4D, the density is gradually increasing. Yes, density has to increasing. But that 4D to 5D, density is almost becoming what? Double. Density is what? Becoming double. 3D to 4D, normal increase in the density, but 4D to 5D, the density is almost becoming double. It is also due to lanthanide contraction effect. See, 3D to 4D atomic size has to increasing, but 4D to 5D atomic size instead of increasing, it is decreasing or remaining more or less same. First point. Coming to the second point, 3D to 4D density is increasing, but 4D to 5D density is almost becoming double. It is due to again lanthanide contraction. So, decrease in the atomic size of 5D series, abnormal increase in the densities of this particular 5D series of elements due to lanthanide contraction effect. Coming to the next point, you see, you might be knowing this very well in the case of 30A group. Third A group, consider again fourth A group. Still you can also take a fifth A group of element. Now, in the case of third A group, thallium is exhibiting thallium, lead and bismuth you consider. Thallium, lead and bismuth you consider. Thallium, actually what is the common oxidation number of this particular third A group? Third A group common oxidation number should be +3, fourth A group should be +4, and it should be what? +5. But thallium stable oxidation state we generally found to be, it is actually +1. In the case of lead it is found to be +2. In the case of bismuth it is found to be +3. Look at here, thallium, lead and bismuth, their stable oxidation states are what? +1, +2 and +3. This is due to what reason? Inert pair effect. It is due to inert pair effect, this particular inert pair effect. Inert pair effect. This particular three elements are exhibiting lower oxidation number than their group number. This is what to call inert pair effect. The inert pair effect exhibited by this particular thallium, lead and bismuth only due to lanthanide contraction effect. This is due to lanthanide contraction effect. Next. Now as you are saying the atomic sizes or actually atomic size, ionic sizes or atomic sizes are gradually decreasing. When there is a decrease in atomic and ionic sizes, we can see either you consider lanthanide oxides, take lanthanide oxides and lanthanide hydroxide. Either you take lanthanide oxides or lanthanide hydroxide from left to right. From left to right, the basicity is decreasing. Left to right, basicity of this particular lanthanide oxides and hydroxides gradually decreasing. So lanthanide oxides and hydroxide left to right, their basicity is gradually decreasing. Why decreasing? Now once atomic size is decreasing, the strength of lanthanum to OH bond is becoming more. It cannot be easily ionizable. Therefore lanthanum to lutetium, the basics of oxides and hydroxides gradually decreasing. What you can conclude now? Lanthanum hydroxide is what? A stronger base, but lutetium hydroxide is what? A weaker base. Lutetium hydroxide is weaker base. Next, once we are concluding that 4D and 5D elements are having more or less same size, then most of the 4D and 5D elements are available in the same mineral and they are showing much more similarities. Now you consider 4D and 5D elements, 4D and 5D elements. Now it can take here 4D zirconium, niobium, molybdenum, few elements I am showing 4D elements. Next come to 5D. After this particular zirconium, this is particular what? Hafnium, zirconium, niobium, molybdenum, lanthanum, hafnium and tantalum. You take tantalum, you can also consider tungsten. So this particular 4D and 5D elements are having more or less same size. Once atomic size is more or less same, what we can conclude is most of the 4D elements, 5D elements are showing similarities in their properties. When their atomic size is more or less same, they are showing much more similarities in their properties. One more thing is important. Most of the 4D and 5D elements are available in the same mineral. What do you understand by this? Now, wherever zirconium is there, there will be hafnium. Wherever hafnium is there, there will be zirconium. So this particular zirconium and hafnium are having more or less identical sizes. Their properties are same. This is due to lanthanide contraction effect. First one is 3D to 4D size increasing, but 4D to 5D size is decreasing or remaining more or less same. Next, 3D to 4D the density is increasing, but 3D to 4D density is becoming double. This is due to lanthanide contraction. Next, inert pair effect exhibited by thallium, lead and bismuth. Next, there is a gradual decrease in the basics of lanthanide oxides and hydroxides. Next, as the 4D and 5D are having more or less same sizes, then most of the 4D and 5D elements are available in the same mineral and they are showing much more similarities in their properties, especially zirconium and hafnium showing properties similar due to lanthanide contraction effect. This particular point is important. Why zirconium and hafnium are having more or less same size and properties? This is only due to lanthanide contraction effect. Next, let me discuss separation of lanthanides. Separation of lanthanides. Separation of lanthanides. Generally, you take any mineral of lanthanide, generally that is carrying what 2 or more than 2 elements, consider XYZ. But generally we have to separate one of the lanthanide from the other lanthanide. In what way we can separate this particular lanthanide? What are the methods we apply? There may be many methods, but we discuss few methods which are important, which are generally appearing in our entrance exams. Now let us consider the first method. What we can say is ion exchange method. Ion exchange method. Ion exchange method. First method is ion exchange method. Second method is solvent extraction method. Solvent extraction method. Solvent extraction method. Solvent extraction method. And third one is actually precipitation method. Third one, precipitation method. Third one, precipitation method. Precipitation method. Actually, in this particular methods, ion exchange method, solvent extraction, and again precipitation method, mainly questions appearing. Each method is dependent on what factor. That is very important to remember. This ion exchange method is actually based on sizes of hydrated ions. Sizes of hydrated ions. Sizes of hydrated ions. A bigger hydrated ion is actually eluted first, followed by smaller, and smallest. This is dependent on size of hydrated ions. A bigger hydrated ion is eluted or separated first, followed by smaller and smallest ions. This is dependent on sizes of hydrated ion. Coming to the next one, solvent extraction method. This particular solvent extraction method is dependent on solubility of lanthanide salts. Solubility of lanthanide salts. Solubility of lanthanide salts. What is this solubility of lanthanide salt? Some of the lanthanide salts are actually more soluble in organic solvents. Some of the lanthanides are more soluble in organic solvent. Some of the lanthanides are more soluble in what? Aqueous solvents. Aqueous solvent. Based on their solubility, we can separate one lanthanide from the other lanthanide. Next, coming to precipitation method. Precipitation method. This is actually based on basicity of lanthanides, and rate of precipitation. Rate of precipitation. Consider if you take now cerium-2, let me say europium, cerium-2, europium, and europium-2, last element to take lutetium. Now, the cerium-2 lutetium, the basicity of this particular hydroxides, basicities of hydroxides and oxides gradually decreasing. What you can consider this particular second half, the right side of this particular second half of lanthanides are having less basic. These are actually less basic. These are found to be what? More basic. These are actually more basic. These are less basic. These are more basic. These are requiring very less number of hydroxide ions to be precipitated. To precipitate these particular, it is requiring very less number of hydroxide ions. But to precipitate this particular cerium to europium, as their basicity is more, requiring more concentration of hydroxide ion. Suppose you are adding little amount of hydroxide ions to this, then the right hand side of the half, right hand side of this particular lanthanides are rapidly precipitated in comparison to left hand side lanthanide ion. So this particular method is based on the rate of precipitation of hydrated ions. The right hand side, these lanthanides are rapidly precipitated in comparison to left hand side lanthanides. Accordingly, we can separate one lanthanide from the other lanthanide. These are the three methods we apply. What you have to actually remember is each method dependent on what factor. So ion exchange method dependent on sizes of hydrated ions, and solvent extraction method dependent on the solubility of lanthanide salts, whether in organic solvent or aqueous solvent. Means some of the salts are highly soluble in organic solvent, some of the salts are more soluble in aqueous solvent. According to, based on their solubility, we can separate one from the other. The third method is actually based on rate of precipitation of hydroxides. The right hand side lanthanides, what is second half of lanthanides, are actually rapidly precipitated because they are less basic in comparison to left hand side half lanthanides. These are the methods to separate one lanthanide from the other lanthanides.